Imagine a computer solving a problem in 200 seconds that would take our fastest classical supercomputer 10,000 years to calculate. That staggering power traces back to 1981, when physicist Richard Feynman proposed simulating subatomic physics using machines that operate on quantum rules. Classical bits are binary, restricted to 0 or 1, but a quantum bit, or qubit, operates in superposition, meaning it can exist as 0, 1, or a complex combination of both at once, doubling data capacity with every single qubit added to the system. This exponential scaling is a dual-edged sword. It allows us to simulate molecular interactions for drug discovery that are impossible today, but it also provides the raw power to crack the encryption protecting our global digital infrastructure. But these quantum bits are extraordinarily fragile. Even a microscopic change in heat or a single stray photon can cause them to collapse out of their quantum state, a failure known as decoherence.
Because of this instability, the last decade has been defined as the NISQ era, Noisy Intermediate Scale Quantum. These machines are error-prone prototypes, only capable of running brief, highly controlled experiments before the noise takes over. To fight this, engineers suspend processors inside massive dilution refrigerators, cooling the chips to near absolute zero to isolate them from environmental noise. The industry is now shifting its focus towards system stability. While raw qubit counts make headlines, the real engineering frontier lies in the complex architecture needed to keep those particles from collapsing. The solution to this fragility is quantum error correction, or QEC, a specialized architectural layer that filters quantum noise into a clean signal. Engineers distribute information across a grid of noisy physical qubits to form a stable logical qubit. Surrounding qubits absorb and correct any detected anomalies. This achieves the fault tolerance threshold, where adding physical qubits causes the error rate to plummet. Crossing this fault tolerance threshold transforms quantum computing into a scalable engineering discipline. It proves that the system can theoretically expand to any size without being overwhelmed by its own errors. With the math proven, a hardware race is underway to determine which physical modality can best scale these logical qubits into commercial machines. Major tech firms are pursuing the superconducting route, which uses microwave pulses to control artificial atoms on silicon chips. Their primary advantage is the ability to perform operations at high speeds. Other researchers use trapped ion or neutral atom methods, employing precision lasers to suspend individual, uncharged atoms in a vacuum. While superconducting chips are faster, these atomic systems maintain their quantum state for longer periods and have lower baseline error rates, which makes error correction easier to implement. There is no definitive hardware winner yet. The victor will be the architecture that can most efficiently support the millions of error-corrected physical qubits required for a functional system. In practice, quantum computers will work alongside our existing infrastructure in a symbiotic relationship, rather than replacing it. This integration is a technical necessity. Classical supercomputers must monitor the quantum processor in real time, decoding a massive influx of error syndromes at megahertz frequencies with microsecond latency. This is the quantum-centric supercomputer. Standard logic tasks are handled by traditional CPUs and GPUs, while impossible combinatorial bottlenecks are handed off to the quantum processing unit, or QPU. True quantum utility depends on this seamless orchestration. A standalone quantum machine is less useful than one deeply integrated into a high-performance classical network. The current state of this field mirrors the early days of artificial intelligence. We are finishing decades of foundational research that is about to enable a sudden leap in practical capability. By 2030, the goal is to build machines with 10,000 physical qubits. This will move us into the early fault tolerance era, allowing us to run algorithms that have been theoretical for 40 years. Just as early classical computing required room-sized mainframes to perform basic tasks, we are now building massive, sprawling hybrid data centers to house the first generation of error-corrected quantum systems. The underlying architecture of fault tolerance is now verified. Bringing this technology to the global market has moved past the need for a physics miracle. It is now a challenge of industrial-scale manufacturing.